Okay, so today I want to investigate the question of what do we exactly mean when we say general in general relativity. In some sense, we want to specify what we actually mean by general, what we mean by the word general. And in my opinion, I think it's often overlooked that not only do we want to generalize physics to the point where we can say, to the point where we can make a theorem based off of the curvature of space-time, but we also want to generalize the mathematics in some sense. And so what do I mean by that? So what is meant by general? What is meant by, oh, I spelled general, that's embarrassing. Okay. So what is meant by general? General, when we say general relativity. So up until this point, I have been working with objects like the affine connection, the covariant or contravariant vectors, covariant vectors, and I've sort of interchanged these notations with this notation here, f mu and then e mu, and big E mu and E mu, where the dx mu in this case you could see is sort of defined as, I'll make that a little bit nicer, defined as E mu, and the dx mu is defined as E mu, like that. Right, so this is four basis vectors. This is four basis vectors, each of which live in different spaces. So this is a covector because we define the covector as how the components on the covector change, and how those change. And this is a contravariant vector, and the rules are same with those. It's just that it changes in a different way, and the change. Right, the change is often denoted with this gamma. We're not going to talk about that quite yet. Transformations of covariant, contravariant vectors, that's important, and I'll get into that later. But this is an interesting concept now, because we want to now take a look at what would happen if let's just take a look at these contravariant guys, f mu dx mu, like this. Or again, this is synonymous with df mu e mu. These are almost kind of like one and the same thing, but we want to actually parse this out a little bit. And so I want to consider now this f mu curly d mu, like this. What does this look like? Well, this looks like f mu. This is a partial derivative. This is a partial derivative, partial with respect to dx mu. And if we were to write this in full, with all the components, the zeroth component or the time component, dx 0 with respect to time, plus 1 dx 1 plus f2 d dx 2 plus f3 d dx 3. So these are partial derivatives, And that means these things are operators. So what are they operating on? Well, this guy right here is this is just a component, right? These guys right here are just components. But these guys here are operators. These guys here are operators. And so what are they operating on? So we could say, well, maybe they're operating on some multivariable function that exists in four-dimensional space, right? One in space-time. This is the time component. And these guys are the spatial components. Okay? And so this is sort of the x position, the y position, and the z position. But in this case, it's the dx1 position, the dx2 position, and the dx3 position. Right? If we wanted to be a little bit more experimental physicists about this, we could say dx, dy, or dz, where x1 is equal to x, x2 is equal to y, and x3 is equal to z. Okay, and then x0 would be equal to t. Okay, so we can actually put a t right here. This is just a different notation. This here just summarizes all of this into a two-liner, or into a one-liner that's very short and concise. And whenever we see the mu's here, we're summing over them like this. Okay. But again, so let's get back to this notion of these guys here being operators. So these basis vectors, so the basis of the spacetime is operators, but we have to operate on some function, and this is where the generalizability comes into play. Because suppose we had some spacetime. Okay, the spacetime has some curve to it. Right, and so this is a function again that exists in 4D space in a time. So at each point we can define each point as having a location in time, a location in the x direction, a location in the y direction, and a location in the z direction, like that. And we have that for each and every point. So this would be, we would have one here. We would have 4 numbers assigned to this point. We would have 4 numbers assigned to this point, and this point, and so on. Right. So this is again a four-dimensional manifold. Right? And this is what this kind of gets into manifold calculus and all this kind of stuff. But right now, this is just a four-dimensional function, right? And it's a four-dimensional function, or in other words, oftentimes the way I like to think about this is not a 4D function, or there might be some different names to this, or a 4D. In physics speak, it's a 4D manifold, or in abstract algebra speak, 4D manifold. And the other way to say 4 dimensions, it's always hard for us to visualize 4 dimensions. So the other way to think about this, the way I like to think about it, is for a 4-component function. It's a function that has 4 components to it. And by saying 4 components, we open ourselves up to sort of a new way of thinking about dimensionality, right? And this is gonna play a huge role not just in GR, but in so many other areas of physics where we want to say, suppose we could all of a sudden begin to visualize, in some sense, what a 6-dimensional space might look like, right? Well, perhaps not might look like, but what we can begin to visualize it in some mathematical sense, right? So a 6-dimensional space is synonymous with saying that the space at each point has 6 components. And so in order to describe the space at every location in time, at every location, we have to specify 6 numbers. Okay, in a 4D case, we have to specify 4 numbers, i.e. the time component, the x and the xyz components. In 3D space, that one's easy to visualize. This one has 3 components, right? It has the x, y, and z component. So this is a sort of new way of thinking about dimensionality that will most likely help us in understanding GR. Okay, but let's get back to these derivatives, these partial derivatives. So suppose now we have a 4-component function that defines the curvature of our space. Okay, and again we have the metric tensor at all these locations. We have whole entire vector spaces. We have covector spaces. We have dual spaces. We've talked about that now. But now suppose we want to, just by virtue of having this structure, by having this manifold-like structure, we can this will help us define what our basis is at each point, because these here are sort of independent of each other, right? Just like the components or the dimensionality of your Cartesian, of any Cartesian plane is orthogonal to one another, right? These taking the time component of a function is, you don't need to know anything about the spatial components of this function if we were to take derivatives like or partial derivatives like this. So we could have some multivariate function. Again, we can have some multivariate function that looks like f. It's a function of t, x, y, and z. Okay. Suppose it looks something crazy like t squared plus the square root of tx plus yz. All right. Well, in this case, d dt is equal of f is equal to 2t plus the square root of x. Okay. Dx of f would be the square root of t, and that's it, square root of t. And so on, we could do dx y dx c. But notice now, if this was our function that defined our manifold, right? If this was our function, this now here, so these operators have to act on some function that defines some notion of our space, what our space actually looks like, right? And these are the bases, right? So this becomes the basis for our for our space. So in some sense, the function itself sort of defines what our bases are going to look like. This is our manifold basis. Our manifold basis, because we have a manifold F, or we have some manifold F, and it's got 4 components to it, and this is what its basis, this is what its time component basis looks like. Okay. So again, then we'd have to specify a value for t. We'd have to specify a value for x to get some number, right? And then we'd slap in front of this. So this is our basis. We'd slap in front of this f0, right? So in sort of summation here, we have this formula. We have some function that defines the notion of what our manifold looks like, and these derivatives now become the basis, right? So the function itself sort of endows a basis, and then we slap on these components to understand how vectors change as they travel along that basis, right? So in total now, we have f mu nu, we have this guy. This is what is dealt with a lot. So I'll actually redraw this. We have f mu d mu. So suppose now, so a tensor in this space, say a rank 1, 3, or a rank 1, 2 tensor, mu nu lambda, for example, right? So that would be d mu. Okay, these two guys here, these are covariant. Well, okay, this is another concept we have to go over. So its basis is actually going to be dx mu and then dx nu, or lambda. Right, so in some sense, this is like, if we could kind of think of this as these guys are the bases for our covariant space, and this guy is the basis for our contravariant space. Okay. Now why? So why is that the case? Well, if you remember, so our contravariant space has to have this covariant basis right here. So this would be dx mu, and then suppose we had suppose we had dx mu like this. All right, well, we can kind of think of one as being kind of like the inverse of the other, right? Or we can think about how these things would transform, right? Again, our dx mu is on the bottom here, right? So this is something that sort of transforms covariantly, and this dx mu here is something that sort of transforms contravariantly. If we recall our discussion on forces and electric fields, we can do the brunt work, and we can see, we'll find that these objects transform just like forces, just like if we were to compare them with the way forces transformed and the way electric fields transformed. And because if you remember, E mu nu, we said this was a covariant object, right? And this covariant object, it was defined by having, I believe it was the charge over the distance, right? And here's something over the distance. As we change that distance, the components will change just like that. And then these guys here, the same logic holds for these guys. So we can see now, there's a very good way we can use calculus. We can embed calculus now into our manifold, because these guys are operators. This guy at least is an operator. This guy is a little distance, right? on that manifold. All right. So that sort of establishes the idea of covariant and contravariant bases and making this realization. This is a realization that we can use dx mu as a basis and dx mu as a basis. This is the realization, and this is what becomes very important, especially when we talk about the spin connection. Like I keep on coming back to the spin connection, because the spin connection is sort of this esoteric thing that a lot of us really want to understand, but it's actually it can be really hard to understand. It's sort of the beginning gateway to understanding stuff like the Wheeler-DeWitt equation. Wheeler, if I could spell this, DeWitt equation. We need and understanding quantum gravity. Right? If we can make this realization, we can begin to understand that this is the manifold basis. This is the manifold basis. We want to understand what the relationship is between the manifold basis and a regular orthogonal basis, right? So if we have regular orthogonal basis, the connection between these two things, we can now, once we can distinguish that there is actually a difference between these guys, which we've established now, and these guys. These are the guys that look like this. They go along each direction. The connection between these guys are these little tetrads. These little tetrads, E, mu, A, in which the mu here is the manifold basis coordinate, and the A here is the orthogonal basis coordinates. Okay. And then the tetrad, so these are tetrads. And that's going to lead us to the spin connection. So with that being said, I will stop this and we'll move on to the next video. Hope to see you there.